The best way to understand a complex system is to open it up and see its structure and see how it works. So the same thing applies to the human brain as well. The Brain Centre at IIT Madras is actually dissecting human brains to understand the structure of the brain and to also perform a 3D map, to carry out a 3D mapping of the brain and better understand the system. So we're joined by Professor Mohan. So sir, please tell us what is the objective of mapping human brains? You're dissecting them to a very small size and then mapping them.
So if you look at it, the brain is one of the ultimate frontiers which we do not understand today. And because we don't understand it, we can't really make significant advancements, not just scientifically, but medically, because we don't have the details of the brain. So that was our, sort of a fundamental motivation when we started this brain center. And the project started in 2020. We started this project. We wanted to create maps, detailed cell resolution maps of human brains, right from fetus all the way to age, all the way to old age, not only across different age group but also across different diseases that afflict them across different ages. So that was the motivation, that was the objective of the project when it started. And what you're seeing today is the first set of data of the second trimester, which is an important development phase both for the brain as well as for the child, for fetus towards a child. So the first set of data is being released today of 5 fetal brains in second trimester, 14 week, 17 week, 21, 22 and 24 week gestational week fetal brain data is being released publicly at cell resolution and 3D.
What are the complexities, especially when it comes to a large adult human brain? It's of a certain size and it's of a certain level of maturity, but fetal brains are very complex to handle. How do you manage it, and what is the technology that goes into dissecting all of this?
So the fetal brain has many challenges. First is the fetal brain is very, very soft and very fragile. So when adult brain is large, that is one type of challenge, but the adult brain is also more rigid, not much more sturdier to handle than the fetal brain. So we had to develop special processes of how to extract this brain from the postmortem fetus. That is the first challenge. Second challenge is how do you freeze such a small and such a fragile brain? Because as you know, when you freeze, water expands, and you can have a damage both at the microcellular level and also at the macro level, because the brain can crack. So we had to do several experiments to figure out what is the right way to actually freeze a brain, and that is the first challenge. And after that, how do you section this brain at a very thin sections, 10 to 20 micron, and do it very reliably, not just do one section and the next 10 sections don't work. So how do you do 4,000 sections, 3 to 4,000 sections of an entire brain, a fetal brain, and transfer it to a glass slide? Right? Because once you section it, it's going to fall. So you'll have to now robotically have a system to pick it up and then transfer it to a glass slide and then use it. I'm using a simplistic term, which is coloring it. Essentially, it is immunohistochemistry. How do you color different cells, cell types, and different antibodies? You do that. Then how do you microscopically image it? But all this has to happen. 3 things has to happen. One is all of them need to happen at high quality. 2, all of them need to happen at a reasonable speed, because only then you can do whole brain. 3rd, all of them need to be automated, which is actually part of the cost thing, part of the quality thing, and also only if you automate it, you can actually keep the cost down. So today we are able to do this at almost 1/10 of the cost of normally what would have taken in the West.
So when you do a 3D mapping of the brain, right, you're taking 2 types of brains. One is a brain which is medically in a fit condition and not, facing any disease. Whereas the other category of brains are those that are with some sort of disease or some sort of disorder. So in that case, how do you manage? In that case, how do you compare, and what do you expect to learn from this comparison between a diseased brain and a, normal condition brain?
So as you know, any pathology needs a baseline of what we call neurotypical. Typically, normally how a brain would be. So if you don't have the neurotypical brain, then when you have a finding in the pathology brains, you don't know how to compare, measure and contrast it. So that is why you need both the neurotypical brain as well as the pathological brain. And so what you're seeing today are neurotypical brains, and we have several pathology brains of various developmental disorders of different kinds, and that also is getting released, that is also getting processed, and we will release those data over the next several months to a year.
Right. So, what are the medical conditions or disorders that you hope to find solutions for in the coming decades when you compare these brains, 3D maps of the normal ones and the ones with some sort of problem?
Yeah. So as I was mentioning, if you look at diseases of the brain, there could be developmental disorders which may start even from the fetus, or some of them may start during childhood. That is developmental disorders of how a child becomes an adult, and then once it's an adult, then there are various other brain-related disorders that may afflict you. Infections like rabies, stroke, and once you get to aging, right, then what we call neurodegenerative conditions, be it dementia, Alzheimer's, Parkinson's, and then you have psychiatric conditions, schizophrenia, and then you have mental retardation, which can actually start from childhood and then go all the way to old age. So these are the different types of brains we have acquired from various medical institutions, and we will be making detailed maps of all this, and we'll be sharing the findings.
So, based on the findings, what sort of medical interventions can be done either at whatever level to ensure that these medical conditions can perhaps be found cured at some point?
Yeah. So, for a medical advancement to happen, you need the scientific advancement, which is basically understanding and seeing the brain. So we have taken the first step. So once this is done, this is already being shared with the medical community. So today we are doing this work in collaboration with various medical practitioners, both in India and abroad. Once it reaches a critical level where these scientific findings are dispersed into the medical research community, then you will start to see the medical advancements. The medical advancements could lead to different ways of doing surgery, or different chemical related treatment, which is basically pharmaceuticals, or some of them may even need a gene therapy. So these are possibilities of how you treat different kinds of things. But we have taken the first step here. So and after this will get into the medical field, and then the medical advancements will happen.
So, as far as the storage is concerned, 3D brain maps, how intense is this storage? How vast is that kind of storage? And you're probably dealing with dozens or more brains. So, what kind of storage capacity and computing muscle power are we looking at for such an operation of massive scale?
Yeah. So, this is actually a significant challenge. I would say, if you ask me, one challenge that still remains, and it will become even a bigger challenge as we become more and more successful, is storage and computing. The adult human brain takes about few petabytes, 3 to 5 petabytes to store. So you can quickly imagine the moment I have 10 adult brains, and we want to actually both process it internally for our analysis and findings, and to make it available to the public, you're talking about 30 to 50 petabytes of storage, and that is significant high storage. And the compute part of it, because you're talking about analyzing at cellular level, which is about a kilobyte, you can say, across several petabytes. So you need heavy computing, both CPU and GPU, and all of these need to happen at a reasonably parallel manner, because we cannot say that it will take us 1 year to process a brain computationally, because then we will not be able to scale this quickly, and we want this data to be out there in the public, and we want the advancements to happen. So that is a significant challenge. So we actually appeal to the technology players, starting from hardware, computing, storage, IT services. We need support from all of you to scale this into hundreds of petabytes of storage, and the necessary compute to analyze these hundreds of petabytes at a resolution of kilobytes, and all of this at a reasonably fast pace, which is we actually we want the brain data to be analyzed at at the speed of 1 brain per month. Today we are able to physically process the data, physically process the brain, and generate the data at almost a brain per month as a pipeline. But we want the computation to also happen, so that these analyses can be sped up and accelerated, and these results can come out.
So also, what percentage of this operation is indigenously done as far as the technology goes and as far as the methods are concerned?
Yeah. So the the technology, the many pieces of technology which we talked about, the physical processing of, how do you freeze a brain, how do you section a brain, how do you transfer it into glass sections, and how do you do a staining of it. Many of these technologies don't exist, so we had to develop all of them. The software which you see, how do you see a petabyte level thing, a petabyte level volume without any supercomputer, just with your laptop and a phone, and that is something we needed to create this special software so that this can be done. So that is, we had to create several technology pieces around it. And of course, as I was saying, computing remains a significant challenge, and we want help from industry players to come in and do this in a significant level. Thank you very much.
That was Professor Mohan telling us about the multidisciplinary work that's carried out at the IIT Madras Brain Centre. It brings together neuroscience, engineering, medicine, and computing. All of that's coming together to break and ensure that there's better treatments and better methods that can be evolved in medical sciences, particularly with regards brain treatments. From Chennai, Siddharth MP, WION World is One.